Ammonia production, the combining of hydrogen and nitrogen to form ammonia gas, requires utilizing a variety of process equipment to produce the end product. Without question, the most important process component is the primary reformer used to convert natural gas and steam into hydrogen. The primary reformer, or reforming furnace, is divided into two identical refractory lined cells, each fitted with vertically aligned radiant tubes filled with catalyst. Steam and natural gas is converted into hydrogen in the presence of this catalyst and high temperatures in these radiant tubes. Heat for reaction is provided by main burners located at two terrace levels on both sides of each cell, and convection section auxiliary burners located above the cells. Natural gas is the main fuel supply, with high hydrogen content purge gas from the synthesis unit added once the entire unit is online. The reformer, located at the front end of the process, governs all downstream component operation. This requires proper furnace control at all times, ensuring ideal process conditions. Furnace firing procedures are a series of steps performed in starting and getting the reformer effectively and efficiently to ideal operating conditions. The sequence is always similar, but can begin at any point regardless of how far a shutdown was taken. A cold start or completely down. A hot start with steam in, or at any point up to full operating capacity. Prior to a cold startup, a complete inspection of the entire reformer is carried out, ensuring all controls are in order. If maintenance work was completed, examine the repairs for completeness and check for tools or debris possibly left behind. Always ensure the area is safe and ready for startup before indicating to the console operator that you are ready to begin. On a shutdown, fuel gas systems may be exposed to atmospheric air. This necessitates purging the lines with nitrogen for air removal, as a combination of air and fuel gas is highly explosive. The nitrogen purge is put on the fuel gas system at battery limits bleed valve connection on the downstream side to PICV 103. The following field moves are made in commissioning a nitrogen purge to the reformer burner headers. Select the proper nitrogen hose from the cabinet and connect and secure the fitting to the bleed valve and local nitrogen station. Contact the console operator once you're prepared to reset the emergency trip valves XVA103 and XV010. Place finger over trip valve solenoid operator while reset is console activated. Hold it until open. Open the bypasses around FICV 110 and 111 and PICV 010 several turns, ensuring a free flow of nitrogen. Nitrogen cannot flow to the upper terrace burners until RCV 110 and 111 are reset as follows. Contact the console operator once you're prepared to reset the valves. Proceed to the local reset control next to RCV 111. After the console activated switch is in the run position, flip the switch lever using the attached pin. During normal operation, reformer fuel gas headers feed the main and auxiliary burners in both reformer cells and the convection section. While purging, the 4 bleed valves on terrace 1 and 2 headers and the auxiliary header must be closed and plugged. Finally, ensure all reformer burner control valves are closed prior to commissioning the nitrogen purge on the fuel gas system at PICV 103. Pressure up the system to about 75 pounds, indicated on the gauge mounted to PICV 103 output line. Once pressured up, block in the nitrogen purge to the system. Now, open the bleed valve on PICV 103 output line, depressurizing system to about 10 pounds. This procedure is performed 3 times over a half-hour period, ensuring all air is removed from the system. Finally, repressurize the system prior to starting one ID fan to purge the reformer. En route to the ID fans on top of the primary reformer, open the burner air registers on the first terrace and ensure those on 2 and 3 are closed. Now, climb to the top of the reformer to start one ID fan required to draw air through the lower terrace burner registers, purging the furnace. ID fan startup procedures are carried out as follows. Check for proper lube oil level. Then, turn on the electric oil heater, warming the oil to 80 degrees Fahrenheit. Start the electric oil pump, ensuring full circulation before slowly opening the turbine exhaust steam valve, allowing back pressure to warm the turbine. Open the turbine casing and 600-pound steam inlet line condensate drains and reset the turbine trip lever. Check all equipment before contacting the console operator, requesting minimum speed setting on the turbine governor control. Ensure the damper on the fan to be started is the only one open.
Okay, Richard, I got the ID fan set for minimum governor. You can bring her up now.
Crack open the 600-pound steam inlet valve slowly, allowing the turbine to slow roll for about 10 minutes. Close the condensate drains and inform the console operator that the turbine is ready for full operation. Open the 600-pound steam inlet valve wide and unblock the 600-pound line to the turbine lube oil pump. Finally, shut down the electric lube oil pump, setting it on standby. The ID fan must run at least 5 minutes with the damper open to purge the furnace of combustible gas. Finally, depressurize the nitrogen in the fuel gas system by opening a bleed valve or furnace burner to complete the purging procedure. The nitrogen hose station is turned off and the hose replaced in the cabinet. The fuel gas system is now ready for commissioning. The field operator positions himself at the battery limit block valve, slowly cracking it open on instructions from the console operator. Gas flows to PICV 103 console-controlled valve, establishing 125 psig line pressure on the system prior to E134X preheat exchanger during normal operation. 185-pound steam is commissioned to E134X by the field operator before the console operator releases fuel gas at PICV 103 at low pressures of 40 to 50 psig for furnace firing. Fuel gas must be preheated to 175 degrees Fahrenheit by 185-pound steam in E134X to avoid carbamate formation in lines and instruments. Carbamate particles form if carbon dioxide in natural gas and ammonia in purge gas are united at temperatures below 100 degrees Fahrenheit. The fuel gas flows from E134X to D118, the knockout drum for moisture removal, prior to flowing through FICV 110 and 111, feeding the main burners of both furnace cells. Radiant tube outlet temperature is held at 1420 degrees Fahrenheit by console-monitored temperature sensors, controlling flow at FICV 110 and 111 during normal operation. Fuel flow to the auxiliary burners, controlled by PICV 010, maintains a temperature of 685 degrees Fahrenheit on the steam coils in the convection section during normal operation. The furnace is now ready for firing. The operator makes a final walk-around inspection, ensuring everything is in order before contacting the console operator, indicating he is ready to begin. The procedure for furnace firing is as follows. Ensure all burner fuel shutoff valves are closed and the 600-pound steam from the utilities plant is available to the reformer superheat coils. With the block valves and main bypass valves closed, open FICV 110 and 111 and PICV 010 minimum flow valves 2 turns, delivering fuel gas to 9 headers on all 3 terraces. Burners are lit in sequence on terrace 1 first, 2 burners on one cell side, then 2 on the other side of the cell. This pattern is repeated on cell 2, ensuring even heating throughout the furnace and preventing radiant tube warpage. 2 auxiliary burners are lit to warm steam in the convection section to 650 degrees Fahrenheit in preparation for compressor C102 startup. Second terrace burners are not lit until well into startup. Burner lighting is accomplished as follows. Light the propane torch and stabilize the flame. Direct the torch flame into the air register and slowly open the burner fuel shutoff valve at the same time. View the flame through the air register or port and adjust the shutoff valve to establish a flame of no more than 6 inches. Now close the air register to an opening of about 1 inch. This procedure is followed for all burner lighting. The field operator is instructed by the console operator on how many burners to light and when to light them as the furnace temperatures increase. Never light one burner off another or off hot brickwork as fuel accumulates near the burners, resulting in explosion and possible personal injury. If the first burner fails to light, shut off the fuel valve and allow the ID fan to purge the furnace for 5 minutes before attempting to relight the burner. While waiting, check the position of fuel trip valves and the fuel system for proper operation. Once the initial main and auxiliary burners are lit, C102 air compressor is put online to warm the reformer to approximately 300 degrees Fahrenheit with air to bring the catalyst above the steam condensation point. At this temperature, 600-pound steam is commissioned to the radiant tubes and firing increased to warm the tubes at 50 degrees Fahrenheit per hour. As the reformer temperature increases, more burners are lit. The field operator maintains low convection section arch temperature by keeping the fuel pressures lower to top burners than bottom, while maintaining equal pressure to the cells on each terrace. Fuel pressure is maintained between 4 and 8 psig by adjusting the burner header globe valves. Once fuel requirements exceed the minimum flow supply, FICV 110 and 111 are unblocked, giving the console operator minimum control of pressure and flow. The convection section temperatures begin to increase and require second ID fan to be started as the arch temperature approaches 400 degrees Fahrenheit. The second ID fan is started as the first. The entire startup may take up to 24 hours before all burners are lit. During this time, the furnace is trimmed, ensuring header fuel pressures are equal on each terrace, within 4 to 8 psig for the main burners and not exceeding 12 psig on the auxiliary burners. Excess oxygen levels are controlled at 1 to 2% in flue gas by adjusting ID fan speed and air register opening while keeping the furnace draft at 0.1 to 0.15 inches of water. The console operator adjusts the ID fan speed with dampers wide open and the field operators adjust the registers. Ideal furnace operation is achieved through a combination of precise fuel gas pressure, correct air register opening, and proper ID fan speeds. Small changes in any of these variables has significant effect on furnace conditions. Once fuel pressure, draft, and excess oxygen are properly set, furnace temperatures are balanced by adjusting the air register openings. The objective is to have radiant tube temperatures equal for the entire tube length, as well as equal temperatures laterally across each cell. Increasing register openings draws heat to the furnace top, while closing the registers heats the lower portion of the furnace. If the lower terrace temperature is determined to be low, registers are closed from 1/4 to 1/8 of an inch. The flame is checked for proper combustion, maintaining a negative pressure at the bottom terrace inspection doors. Remember, adjust only one variable at a time and allow the furnace to react and stabilize before making another adjustment. About 48 to 72 hours after the reformer is back online, purge gas from the synthesis section is commissioned to the reformer. Purge gas is introduced into the reformer fuel gas system as follows. The console operator indicates the system is ready to be put online. The field operator slowly opens the purge gas to fuel gas isolation valve when instructed to. The console operator raises the set point of FICV 121 to close FICV 121A and B to the vent, forcing purge gas to flow into the furnace due to back pressure. The field operator must ensure FICV 121 bypass is closed. Furnace trimming is required after commissioning the purge gas, as it burns with a shorter, bluer flame and has a lower BTU content than natural gas. Once the reformer is properly trimmed, few adjustments are made, just continual monitoring and inspection. Numerous checks, inspections, and adjustments are made to the ID fan systems during normal operations. Furnace draft is controlled from the console by adjusting the ID fan turbine speed at RCS 013 and 14, while RCS 011 and 012 hold dampers wide open. Ideally, both ID fans run at the same speed and registers adjusted to maintain equal negative arch pressures. If they are not equal, furnace draft from one end to the other is uneven, resulting in uneven temperatures on the radiant tube tops. The field operator monitors the ID fan lube oil temperatures by throttling the bypass valve to keep the oil temperatures at 100 degrees Fahrenheit under varying ambient temperatures. Lower than 10 psig indicates a plugged oil filter, a possible lube oil pump malfunction, or possible low oil level. Check the reservoir oil level on the dipstick, adding lubricant if necessary. If this does not correct the problem, the oil filter must be changed by a maintenance technician. If the filter is not changed, or the lube oil pressure continues to drop to 8 psig, the electric backup pump starts. On a continued pressure drop to 4.8 psig, a console alarm sounds with the ID fan turbine tripping at 3 psig. Reformer furnace inspections include checking the main burner flames for proper adjustment. A long flame or a flame impingement can come in contact with the radiant tube, overheating it and eventually causing a tube rupture. Escaping ignited gases from a rupture act as a cutting torch on the adjacent tube, possibly cutting through it. Flame impingement is also caused by fallen brickwork and dirty burner orifices. Dirty burners are shut off and removed for cleaning by a maintenance technician with the field operator's assistance. Flame impingement in the convection section is caused by fuel pressure exceeding 12 psig, as well as dirty burners. If this occurs, check the pressure gauge and adjust or reduce the firing to correct the condition. Long yellow flames cause carbon buildup on the brickwork, lowering fuel efficiency and radiant tube temperature. Adjusting the fuel flow and air registers cures this problem. Radiant tube and furnace hot spots are checked with an optical pyrometer. Temperatures must not exceed 1700 degrees Fahrenheit or furnace and structural damage results. Shooting tubes with an optical pyrometer is completed as follows. Engage the test button, observing the green light indicating the charge. On a low reading, the pyrometer is recharged in the battery charger before use. Open the furnace inspection door and cut back the flames on two burners only to avoid interference with the pyrometer reading. Set the heat range selector dial on the pyrometer front, aligning the letter L with the index mark. Hold the pyrometer to your eye. Aim at radiant tube center and adjust the object lens until the tube and lamp filament are in focus. The focusing ring by the eye shield provides additional adjustment. Press the trigger and adjust the heat scale knob on the pyrometer side until the filament disappears into the target image. Remove and note the pyrometer temperature reading from the L scale on the log sheet. Report any temperature above 1700 degrees Fahrenheit. Watch for hot brickwork or white-hot insulation on tubes as they give false readings. When finished, close the inspection door, open the fuel shutoff valves, and proceed to the next inspection door. The console operator monitors reformer temperature profiles on the console. Temperature deviations exceeding 1700 degrees Fahrenheit on the reformer cells and 1800 degrees Fahrenheit on the arches are corrected in the field by balancing fuel pressure, adjusting registers, or draft by adjusting ID fan speed. Peeling paint on the reformer exterior walls indicates furnace interior wall hotspots over 450 degrees Fahrenheit caused by missing or cracked brickwork. Burnout is prevented by directing steam on the spot for cooling. A pink haze seen inside the upper portion of the furnace indicates poor combustion, a buildup of carbon monoxide, and a potential for internal furnace explosion. A light blue flame around the top of the radiant tube, or carbon monoxide afterburning, indicates the same problem. ID fan speed, proper air register settings, and excess oxygen avoid this situation. Hold a cloth in front of an open air register and observe if it is drawn inward. If not, further register adjustments are required.